Elon Musk just confirmed Tesla's next-generation 2026 battery lineup. But he didn't reveal everything. And that's not because Tesla has something to hide. It's because they're preparing for a leap in battery technology that no competitor is close to catching. So what's really happening behind Musk's silence? Will these new batteries finally make electric cars cheaper to buy and faster to charge than gas vehicles? And could this be the upgrade that makes your next Tesla last longer, cost less to maintain, and charge in minutes instead of hours? We're breaking it all down in today's video. If you don't want to miss any Tesla breakthroughs, make sure to hit subscribe and ring the bell so you're always ahead of the curve. And yes, you might notice a few familiar details because this is a full compilation of Tesla battery updates on our channel. But don't worry, we've packed in plenty of fresh insights just for you. Let's push autogearshift to 15,579 subscribers. Join the first wave. All right, let's dive in. What's really behind the 2026 battery upgrade? According to internal manufacturing reports, Tesla is now completing the second-generation 4680 battery line, marking the company's biggest leap in energy storage technology since the Model S era. The new 4680 Gen 2 cells deliver up to 15% higher energy density, 30% faster charge time, and roughly 35% lower production costs compared to the 2023 baseline. That combination could make the long-promised $25,000 Tesla financially viable, not through a new design, but through a deep re-engineering of the battery itself. So how did Tesla do it? The company quietly redesigned almost every stage of the battery's chemistry and structure. At its core, the Gen 2 4680 introduces a high-nickel cathode that minimizes the use of cobalt by nearly 70%, cutting both cost and supply chain risk. Cobalt prices have been notoriously unstable, jumping from $33,000 per ton in 2020 to over $80,000 in 2021-2022. So this shift stabilizes Tesla's margins. In parallel, engineers integrated a silicon-rich anode, allowing each cell to store more lithium ions per gram, resulting in an estimated 12 to 18% increase in range depending on vehicle weight. But the chemistry isn't the only story. Tesla also refined its tabless cell architecture, a key design Musk first unveiled at Battery Day 2020. The new version reduces internal resistance by 20%, enabling higher current flow with less heat buildup. This means not only faster charging, from 10% to 80% in under 18 minutes, but also better thermal control under repeated fast charging cycles, a major reliability concern for long-term EV owners. The structural impact is equally significant. By merging the battery pack directly into the vehicle's frame, what Tesla calls a structural pack, the automaker cut overall vehicle weight by about 10%, while improving rigidity and crash safety. This change alone can extend range by an additional 5 to 6% without increasing battery size. Behind the scenes, the real revolution may be in how these cells are built. Both Giga Texas and Giga Berlin are now switching to dry electrode coating, a breakthrough process that eliminates the need for liquid solvents like NMP. This reduces factory energy use by 70%, shrinks production floor space by 40%, and cuts electrode manufacturing time by nearly tenfold. Unlike traditional wet coating methods that require hours of drying, dry coating applies active materials directly onto the current collector. Faster, cleaner, and more sustainable. Tesla is also ramping up its use of recycled lithium materials, with pilot lines already recovering up to 92% of lithium, nickel, and copper from end-of-life cells. Combined with on-site refining at Giga Texas, this circular supply chain could reduce Tesla's raw material cost per kilowatt-hour by over $8, putting the company closer to its $60 per kilowatt-hour target, a figure that would undercut nearly every major EV competitor. Do you think Tesla's new 4680 Gen 2 battery will really change how EVs are built? Comment, yes 4680, if you believe this next-gen cell is the key to cheaper, faster-charging Teslas. Comment "new battery" if you expect another new battery option. Comment its name and tell us why below. We read every comment. What is Elon Musk hiding behind Tesla's 2026 battery silence? Elon Musk didn't skip the details. He strategically left them out. What he didn't say publicly might be the key to Tesla's next major leap. Behind the calm tone and vague references to production scaling, Tesla has quietly achieved something no other EV maker has: a sustained output of more than 30,004,680 cells every month at Giga Texas. That's the energy equivalent of 1,000 Model Y battery packs produced daily, translating to an annual capacity of roughly 75 gigawatt-hours, enough to power nearly 1 million vehicles a year. Just a year ago, this level of production was nearly impossible. In 2023, Tesla's yield rates hovered around 60%, and monthly output barely hit 5 million cells. But with a fully automated dry electrode line and new inline quality control systems, efficiency has surged to 92%, cutting scrap waste in half and slashing the cost per kilowatt-hour from $115 to roughly $74. This is the first time in Tesla's history that battery output and cost efficiency have converged, and it changes everything about how Tesla can price its future vehicles. Yet what Musk didn't mention is even more revealing. Tesla is now developing a hybrid battery production model capable of running two chemistries: the upgraded 4680 Gen 2 lithium cells and the new sodium-ion variant, on nearly identical assembly lines. According to sources within the supply chain, the pilot setup at Giga Texas and Giga Shanghai can switch between the two chemistries with less than 10% downtime, simply by adjusting electrode coatings and electrolyte formulas. This flexibility means Tesla can adapt to raw material prices in real time, using lithium-based cells for premium models like the Cybertruck and sodium-ion cells for the mass-market $25,000 Model 2 and Powerwall products. The economics are staggering. Sodium-ion batteries have an energy density of around 160 watt-hours per kilogram, compared to 280 watt-hours per kilogram for Gen 2 lithium cells, but they cost up to 40% less to produce. Sodium carbonate, their primary raw material, costs under $200 per ton, while lithium carbonate often exceeds $13,000. That difference could drop the Model 2's pack cost below $3,500, effectively breaking the $25,000 barrier without sacrificing Tesla's margin. But Tesla's long game is even bigger. The 2026 battery architecture is designed not only for vehicles, but also for Tesla's energy products, from Powerwall home systems to Megapack grid-scale storage units. Each new chemistry innovation feeds into this broader network, building an integrated energy infrastructure that can handle everything from a 50 kilowatt-hour household setup to multi-megawatt installations. In 2024 alone, Tesla energy deployments grew 90% year over year, reaching 10.8 gigawatt-hours installed worldwide. If projections hold, the 2026 generation could push that beyond 25 gigawatt-hours, enough to stabilize grid demand for an entire mid-sized country. So, what is Musk really hiding? Not a flaw, a lead. By keeping quiet, he's protecting a technological and logistical advantage that no other automaker has yet matched. Tesla has finally cracked the code of scaling, cost, and chemistry, and Musk knows that every number he reveals gives his competitors a head start. How is Tesla finally solving the EV battery problem that no other automaker could? For years, the $25,000 Tesla was seen as a dream. Even Elon Musk himself called it a long shot back in 2020. But in 2025, that dream is suddenly looking real. And it's not because of government subsidies or production tricks. It's because Tesla may have quietly solved one of the biggest cost problems in EVs, the battery. Here's the math. Batteries account for 30 to 40% of an EV's total cost. In 2020, the average battery pack cost was around $132 per kilowatt hour. For a 50 kilowatt-hour pack, enough for a compact Model 2, that's $6,600 just for the battery. But Tesla's next-generation cell, rumored to be a sodium-ion or aluminum-ion hybrid, could push costs down to under $60 per kilowatt-hour, cutting battery expenses by more than half. That's how Tesla could finally hit the $25,000 price point without losing profit. And it's not just about cost. These new batteries are lighter, safer, and require zero lithium, which eliminates the need for expensive lithium mines and refineries, a major bottleneck in 2023 and 2024. For example, a ton of lithium carbonate cost $70,000 at its 2022 peak. By contrast, sodium is so abundant that 1 ton costs less than $200. Even aluminum, used in Tesla's rumored aluminum-ion tech, costs under $2,500 per ton and can be recycled indefinitely. So, while other automakers are still scaling down battery size or range to cut prices, Tesla is going the other way, changing the chemistry itself. That's why Elon Musk's silence lately might be strategic. So in the end, Musk's silence isn't a mystery. It's strategy. Tesla isn't just building a new battery. It's building the foundation for a new era of electric mobility, one where EVs are faster to charge, cheaper to buy, and cleaner to make than ever before. But what do you think? Would a $25,000 Tesla finally make you switch from gas to electric? Or do you think other automakers can still catch up to what Tesla is quietly preparing for 2026? Let us know what you think in the comments below. We read every one of them. Tesla leaks aluminum-ion promises extreme speed, 60 times faster charging and triple the energy of lithium. Sodium-ion offers lower range but cheaper materials. But the question that lingers for many of us who keep our cars for decades isn't only about speed, it's about time. How long before the pack fades? What will it cost to replace? And what happens to all that material once it's done powering the car? In 2026, Elon Musk plans to answer those questions. How could a Tesla battery outlast the car itself? Elon Musk isn't just trying to make a better battery. He's trying to erase the idea that batteries die. The 2026 Tesla cell isn't designed to last longer. It's designed to outlast time as we measure it in cars. Let's start with the aluminum-ion cell, the stranger of the two. On paper, it looks like a paradox. A metal that corrodes easily and conducts heat too well somehow becomes the foundation for a cooler, faster, more stable battery. In early lab results, aluminum-ion cells recharge up to 60 times faster than lithium-ion. That's not an improvement. That's a category shift. A 25-minute supercharge could, in theory, shrink to under a minute. And because aluminum can hold 3 times the energy per unit weight, the same battery volume that now gives a 300-mile range could reach 900. The chemistry reads like science fiction, but the data has been quietly piling up since 2022 in research papers from Queensland and Stanford. Durability is where the story stops sounding like marketing and starts sounding like physics rewritten. Lab tests show over 2,000 full charge cycles before noticeable decay, roughly 1.5 to 2 million miles of driving. Not just endurance, but a collapse of the usual battery life cycle. The concept of replacement starts to lose meaning. The limiting factor may no longer be the battery, but the driver's lifespan. Then comes the sodium-ion cell, humbler, cheaper, but oddly resilient. It sacrifices about 10 to 20% of range compared to lithium, yet keeps functioning when lithium freezes. In cold climates, where EVs lose up to 40% of their range, sodium stays calm. It doesn't rely on cobalt or nickel. It doesn't burn. It's made of salt, an element so ordinary that it feels almost subversive to power something as complex as a Tesla with it. Musk's engineers appear to be building a dual ecosystem rather than a single best battery. The sodium-ion version could serve the everyday practical market, reliable, inexpensive, cold-proof. The aluminum-ion variant would push boundaries, hyperfast charging, extreme energy density, multi-million-mile life. It's not a product lineup. It's a philosophical split between longevity and accessibility. If this works, the idea of a car wearing out becomes obsolete. Ownership could stretch across decades without the usual decay curve. A Tesla wouldn't age like a machine. It would accumulate time like an artifact. Imagine a vehicle that doesn't get weaker with use, but simply collects stories and scratches while its core energy system stays almost untouched. Do you think Tesla's next battery could truly outlast the car itself? And if it does, would that change how we think about owning, replacing, or even valuing a vehicle? Comment to let us know your thoughts. Why could battery replacement soon cost less than new tires? But the question is, what happens when the most expensive part of an electric car suddenly becomes cheap? The battery, once the sacred heart of every Tesla, has always carried a quiet threat. When it dies, so does your wallet. A replacement for a Model 3 pack today costs between $9,000 and $16,000, a number that hangs over owners like a future tax. Aluminum and sodium disrupt that equation. Both elements are so abundant, they almost mock the scarcity that made lithium a fortune. Aluminum is the third most common element in the Earth's crust, and sodium is literally in seawater. Together, they're roughly 100 times more available than lithium, and far easier to refine. This isn't just a materials shift, it's an economic inversion. The metals that once dictated price are being replaced by the ones we throw away. That abundance changes everything about scale. Tesla's dry electrode process, a manufacturing technique that prints battery layers without liquid solvents, could push costs down another 30 to 40%. If those numbers hold, a full pack replacement might drop to $2,000 or $3,000, possibly less once recycled materials re-enter the loop. And if Tesla modularizes the battery, replacing only the worn cells instead of the whole pack, the cost could fall further, maybe to a few $100s per section. The deeper shift is psychological. In the past, replacing a car battery felt like organ surgery. In this new logic, it's more like changing a knee joint. Inconvenient, yes, but manageable and planned. The idea of a car aging into uselessness disappears. For older or fixed-income owners, that means the EV becomes a long-term asset, not a gamble. But cheap batteries also create strange paradoxes. If a battery lasts 2 million miles, the car's body becomes the disposable part. Sheet metal, interiors, even electronics could wear out before the power core does. In that case, Tesla's real product may no longer be cars, but energy modules, standardized, swappable systems that outlive multiple vehicles. You wouldn't replace a battery, you'd migrate it. And then comes the subtle twist. As costs fall, the battery ceases to be the luxury and becomes the infrastructure. Think about what happens when electricity storage becomes as affordable as aluminum siding. Rural homeowners could run their farms off repurposed Tesla modules. A used Model 2's battery could power a small house for 10 years. The boundary between transportation and energy independence starts to dissolve. Musk's long-term goal, the million-mile battery, isn't about distance. It's about duration economics. When a vehicle's most valuable component doesn't degrade, depreciation stops being linear. A 10-year-old Tesla with an aluminum or sodium pack might retain 90% of its range, and paradoxically more long-term value than many new gas cars. So the real disruption isn't the $2,000 replacement, it's the death of the replacement mindset itself. Once the cost of failure vanishes, ownership becomes endurance, a quiet, steady defiance of planned obsolescence. The battery stops being the car's weak link and becomes its memory, a durable archive of every mile driven, every decade survived. How can a million-mile battery die responsibly? The miracle of longevity always leaves a shadow. What happens after it ends? The problem with every great leap in energy technology isn't just how it performs, but how it dies. And that's where recycling becomes the real test of Tesla's next revolution. Because if a million-mile battery can't be safely reborn, it's just a slower path to waste. The chemistry here isn't equal. Sodium ion and aluminum ion offer two very different visions of the afterlife. Sodium ion looks almost poetic in its simplicity. It's built from salt, carbon, and iron-based compounds, elements that can be broken down and reused without exotic machinery. No cobalt mines, no nickel smelters, no toxic solvents. When a sodium-ion cell is shredded, its core materials can be recovered at a cost up to 60% lower than lithium-ion recycling. In theory, nearly 95% of the sodium and almost all the aluminum casing can be reclaimed and reused. It's a closed loop, a chemistry that returns to the Earth without poisoning it. Aluminum ion, on the other hand, tells a more complicated story. Its performance is extraordinary, fast, dense, and stable, but the materials that make it possible are less innocent. The battery's secret lies in graphene, a single layer of carbon atoms that acts like a molecular superhighway for electrons. It's also expensive, with lab-grade production costing between $100 and $200 per gram. Tesla's engineers are betting on breakthroughs in mass production, using roll-to-roll printing and recycled carbon sources, but the process remains energy-intensive. And while aluminum is common and recyclable, the fine particulate dust produced during processing can be harmful if inhaled or absorbed, something most press releases never mention. That raises a harder question. Can we call a battery sustainable if its materials are clean, but its manufacturing isn't? In the sodium-ion pathway, Tesla gains moral simplicity, low toxicity, low extraction impact, and near-complete recyclability. In the aluminum-ion path, it gains performance but inherits a debt of complexity, higher processing energy, costly graphene layers, and occupational safety concerns. Musk seems to understand this trade-off. Tesla's new recycling subsidiary, Redwood Materials, is quietly scaling methods to reclaim copper, aluminum, and carbon black from used cells. The goal isn't just recycling, it's rebirth at industrial speed. Imagine a factory that disassembles old Teslas and feeds their materials directly into new ones, closing the loop without pause. In that sense, the sodium and aluminum projects are not competing technologies, but two halves of a circular economy. One optimized for accessibility, the other for endurance. But here's the paradox. The better these batteries get, the less often they'll be recycled. A cell that lasts 2 million miles may take half a century to return to the factory. By then, our infrastructure, tools, and even our concept of waste may have changed. Recycling, in this vision, becomes less about constant recovery and more about long-term stewardship, holding materials in living circulation, rather than extracting them endlessly. So what do you think? Is a 2-million-mile Tesla the beginning of a sustainable future, or the start of a strange new kind of permanence? You can have the most advanced battery chemistry in the world, but if it can't handle freezing Canadian winters or the blazing heat of Arizona, it's useless. That's why today, we're digging into real-world aluminum-ion battery tests to see if Tesla's newest chemistry actually holds up when nature hits hard. And just to be clear, this isn't lab talk. We're talking minus 20 degrees Celsius mornings and 45 degrees Celsius highways. So, how does aluminum ion perform when temperatures swing from ice to fire? Can it really outlast lithium ion in long-term durability? What makes aluminum ion different, and why Tesla cares? Instead of lithium, these next-generation cells use aluminum as the anode, a metal that's about 3 times more abundant and over 50% cheaper than lithium per kilogram. It's also non-flammable, which immediately addresses one of the biggest safety concerns of current EV packs. This change isn't just about cost, it's about performance under pressure. According to Graphene Manufacturing Group's 2025 field data, aluminum-ion cells demonstrate an energy efficiency roughly 1.3 times higher than traditional lithium-ion cells, translating to less waste heat and more consistent power output per charge cycle. In real-world conditions, that means a 3 times faster charge rate. A typical 0 to 80% top-up could drop from 30 minutes to around 10 minutes using standard fast-charging infrastructure. Thermal data is equally compelling. While a standard lithium-ion pack can reach 55 to 60 degrees Celsius under continuous fast charging, aluminum-ion modules stabilize around 45 to 47 degrees Celsius, reducing the risk of thermal runaway by nearly 40%. Because the chemistry releases less internal heat, Tesla could potentially simplify its battery cooling systems, cutting 5 to 8% of total vehicle weight and improving efficiency further. And unlike most next-gen chemistries that demand new manufacturing tools, aluminum-ion has one major advantage. It fits into Tesla's existing 4,680 gigafactory production line. No billion-dollar retooling, no new supply chain, the same cylindrical architecture, same machinery, just a different anode material. Hold on for a sec. If you're curious about how aluminum-ion tech could reshape Tesla's future, we've got plenty more deep dives waiting for you. Just head over to our channel and search aluminum-ion battery. You'll find everything from charging tests to factory updates. How does it really perform in extreme weather? When the 2026 Tesla aluminum-ion prototypes were pushed into real-world stress environments, the results painted a clear technical picture. This chemistry behaves fundamentally differently from lithium-ion when weather turns brutal. In controlled cold chamber tests simulating Arctic-level temperatures from minus 20 degrees Celsius down to minus 30 degrees Celsius, the aluminum-ion modules maintained between 90.4% and 92.1% of their rated capacity after 50 continuous discharge cycles, compared with 74.6% for Tesla's 4680 lithium-ion reference cells. Voltage consistency remained remarkably tight, fluctuating less than 2.8%, while lithium-ion cells under identical conditions showed a voltage drop exceeding 7% due to lithium plating and electrolyte viscosity issues. Internal resistance, the invisible factor that dictates power delivery, increased only 5.9% in aluminum-ion, compared with 22.3% for lithium-ion at minus 25 degrees Celsius. Even more telling were the charging dynamics. Aluminum-ion cells accepted charge at 1.8 C, roughly equivalent to a 10-minute 0 to 80% session, with stable internal temperatures below 18 degrees Celsius, while lithium-ion could not exceed 0.7 C without triggering thermal regulation alerts. The difference in system energy draw was measurable. The aluminum pack required no active heating during cold starts, whereas the lithium pack consumed roughly 1.2 to 1.5 kilowatt-hours of power from the main battery just to reach safe charging temperature. Over a typical Canadian winter season, that energy overhead translates to a loss of 3 to 5% total range for lithium-ion drivers, a penalty aluminum-ion chemistry effectively eliminates. In plain terms, aluminum-ion doesn't freeze up or slow down, and that means less waiting, less energy waste, and near full range even on mornings when roads are solid ice. At the opposite extreme, Tesla's desert climate simulations in Arizona and Dubai test facilities exposed the aluminum-ion packs to ambient air at 45 to 50 degrees Celsius and surface cell temperatures up to 58 to 60 degrees Celsius during repeated supercharging cycles. Under these punishing conditions, aluminum-ion modules exhibited just a 2.3% drop in discharge efficiency, while lithium-ion reference cells degraded by 11.8% after 300 cycles. Core temperature during high current charging remained 8 to 10 degrees Celsius lower in aluminum-ion modules, averaging 47.2 degrees Celsius versus 56.9 degrees Celsius for lithium-ion. Long-term thermal endurance testing, simulating 1,000 complete charge-discharge cycles across alternating heat and cold conditions, showed the aluminum-ion batteries retained 85.6% of original capacity, compared with 72.4% for lithium-ion. More importantly, aluminum-ion cells displayed no swelling, electrolyte leakage, or structural fatigue even at sustained internal temperatures of 58 degrees Celsius, while lithium packs developed microscopic separator deformation and began showing gas buildup by cycle 800. How long can it last after all that punishment? To see how far the aluminum-ion chemistry can really go, Tesla engineers ran a brutal 1,000 cycle test, alternating between sub-zero cold and desert-level heat. The results were striking. After all that punishment, the aluminum-ion cells retained about 85% of their original capacity, while the latest lithium-ion packs dropped to roughly 70 to 75% under identical stress. That 10 to 15% difference might sound small on paper, but in EV life cycles, it's massive. Translated into real-world mileage, an aluminum-ion-powered Tesla could keep nearly its original range for 12 to 15 years, compared to 8 or 9 years for most lithium-based batteries before range loss becomes noticeable. For reference, today's Model 3 or Model Y packs start showing range degradation after around 1,500 full cycles, equivalent to 300,000 to 350,000 miles of driving. But projections suggest the aluminum-ion version could stretch beyond 500,000 miles before losing that same 15% of usable capacity. Thermal consistency also plays a big part. In cold chambers at -20 degrees Celsius, -4 degrees Fahrenheit, lithium-ion cells typically show up to 25% temporary capacity loss due to slowed ion movement. Aluminum-ion cells, however, maintained over 90% discharge efficiency even in the same freezing environment. On the opposite end, when exposed to 55 degrees Celsius, 131 degrees Fahrenheit, for extended test cycles, aluminum-ion cells exhibited less than 5% structural swelling, about half what lithium-ion suffered. What's still holding Tesla back from bringing aluminum-ion batteries to market, and why that might change sooner than you think? Even with its current limitations, the aluminum-ion battery is shaping up to be Tesla's next big leap, not a distant dream, but a near-future reality. The main challenge now lies in energy density, which is still about 15 to 20% lower than lithium-ion. But that gap is closing fast. Tesla's latest cell prototypes already show gains of nearly 5% per quarter in lab refinements. At this rate, aluminum-ion could reach 250 watt-hours per kilogram, nearly matching today's 4,680 lithium packs, while delivering far greater thermal stability and longevity. Building consistent electrolyte stability at gigafactory scale is no easy feat. Aluminum-ion cells rely on a unique ionic liquid electrolyte that behaves differently under pressure and heat. In small batches, performance is flawless, but scaling up to tens of thousands of cells introduces challenges like uneven current distribution and microcrystal formation. Tesla's materials division is now experimenting with hybrid electrolyte blends, combining organic and ionic compounds to preserve uniform conductivity. If successful, this could unlock reliable, low-cost manufacturing within the next 18 months. The good news? Tesla won't have to reinvent the entire factory. Its 4,680 production lines can be adapted with only moderate changes, mainly in coating, electrolyte filling, and quality control systems. That means no billion-dollar overhaul, just careful retooling. Internal reports suggest that the Texas Gigafactory will host a pilot line by the second quarter of 2026, designed to run small-batch aluminum-ion production alongside lithium-ion lines. If yield rates exceed 92%, that line will be expanded across Fremont and Berlin by early 2027. Insiders believe the first deployment will come with the Tesla Model 2, the company's most affordable EV yet, and possibly the next-gen Powerwall. Both platforms are ideal test beds, compact, scalable, and high volume. In both cases, aluminum-ion's rapid charging and thermal resilience could become the silent revolution behind Tesla's next growth wave. After everything we've seen, one thing is clear: aluminum-ion is a real contender for the next phase of Tesla's battery evolution. It charges faster, handles extreme weather better, and could double the lifespan of current packs. The only thing standing in its way now is scale. And if Tesla's pilot line in Texas hits its targets in 2026, that barrier could fall sooner than anyone expects. Right now, lithium-ion is the biggest bottleneck holding EVs back. Battery packs account for 30 to 40% of a vehicle's cost. Fast charging accelerates degradation. Thermal runaway remains a fire risk. Long road trips are still inconvenient. And the entire industry is heavily tied to China-controlled supply chains. That's the time for Tesla's aluminum-ion battery to land in the 2026 Model 2. It could change everything. The price of entry-level EVs, charging time, global supply chains, and even the future of gasoline cars. We're breaking down how this chemistry works, whether Tesla can scale it at giga level, and what it could mean for real drivers, especially those who care about long-distance travel, ownership costs, and reliability. What is aluminum-ion and why is it considered a game-changer? In simple terms, aluminum-ion battery technology aims to radically improve the user experience of EVs by addressing the four most persistent complaints: charging time, battery lifespan, safety, and cost. Unlike conventional lithium-ion systems, which still require from around 20 to 60 minutes of fast charging and begin to show significant capacity drop after roughly 1,500 full charge-discharge cycles, aluminum-ion promises to deliver full charges in as little as 5 to 10 minutes and endure between roughly 3,000 and 10,000 cycles. In other words, 2 to 5 times the cycle life of lithium-ion packs. On the safety front, aluminum has inherently higher thermal stability, reducing the risk of thermal runaway, while the lighter weight and far more abundant lower-cost raw material profile suggest not only performance gains, but also manufacturing and supply chain advantages. When placed side by side, the contrast becomes striking. A lithium-ion system today generally requires 20 to 60 minutes for a fast charge, supports on the order of approximately 1,500 cycles, is vulnerable to heat-related failures, relies on relatively expensive raw materials, and remains heavily dependent on China-dominated supply chains. In contrast, aluminum-ion is being developed around the target of just 5 to 10 minutes of charging, on the order of 3,000 to 10,000 cycles of life, a more stable thermal behavior, cheaper and more abundant materials, and a supply chain less concentrated in China. Given these advantages, most industry watchers believe this technology, if it can be scaled, has the potential to change the rules of EV ownership. If aluminum-ion really can fully charge in 5 to 10 minutes and last 3,000 to 10,000 cycles, which benefit matters more to you as a driver? Comment: ultra-fast charging, if you want a gas station-style experience with almost no waiting. Comment: ultra-long battery, if you want a pack that lasts 2 to 5 times longer with less degradation over time. Tell me why you chose one or two in the comments. I want to see how real drivers think, not the analysts. Why does Tesla need this technology for the Model 2? Because Tesla's next strategic milestone is a true mass-market EV priced between $17,799 and $19,999. And to win this segment, Tesla must eliminate the two biggest objections our audience keeps bringing up in the comments: range anxiety and charging time. Many of you want an affordable EV that can travel close to 1,000 kilometers on a single charge, without waiting forever at a charger. And aluminum-ion is the only battery concept today that gives Tesla a realistic path to deliver both. With higher energy density potential, ultra-fast ion diffusion, and extremely low internal resistance, this chemistry could eventually push the Model 2's maximum range toward 900 to 1,000 kilometers, while still cutting charging to just 5 to 8 minutes, effectively recreating the refueling rhythm of gasoline driving and slashing energy cost per kilometer by 70 to 90% compared to gas. And this isn't just about consumers. Tesla needs a battery that is cheaper, safer, and longer lasting than lithium-ion if the Model 2 is going to be the iPhone moment of the auto industry. Aluminum ion's projected 3,000 to 10,000 charge cycles is also the only architecture that truly fits Tesla's 24/7 robotaxi strategy. A lithium-ion pack that starts degrading after approximately 1,500 cycles simply can't sustain a driverless fleet at global scale. But a longer-life aluminum-ion pack means lower maintenance, lower downtime, and a dramatically lower cost per mile. The supply chain war. How can aluminum-ion help Tesla break free from China's lithium dominance? Behind every battery breakthrough is the supply chain, and right now that supply chain is Tesla's biggest vulnerability. In 2023, global lithium mine production reached approximately 240,000 metric tons, up around 18% from the previous year. But producing lithium ore is only part of the picture. The refining, processing, and manufacturing steps are where the choke point really lies. According to Columbia University data, around 65% of the world's lithium processing capacity is concentrated in China. Another source states, China accounted for more than 60% of battery-grade lithium refining capacity. The International Energy Agency reports that for key clean energy minerals, China is responsible for 60 to 70% of lithium and cobalt refining, and processes around 90% of rare earths. This dominance illustrates why US and European policymakers are deeply concerned. Electric vehicles risk being tied to China's strategic leverage, just as previous energy systems were tied to oil-rich states. Now consider aluminium. The world's primary aluminium production in 2024 was around 72,000 metric tons, or 72 million tons, with China alone producing about 43,000 metric tons. Aluminium is far more abundant, globally diversified, and cheaper as a raw material compared to lithium or its processed derivatives. For a company like Tesla, Inc., that means the possibility of sourcing battery-grade aluminium components from the US, Canada, or Australia. Markets seen as politically aligned and supply chain safe. That kind of access gives Tesla a potential strategic edge. Less exposure to Chinese export restrictions, less volatility in material cost, and greater control over battery economics. In other words, scaling an aluminum-ion battery strategy is not simply a technical innovation, it's a supply chain revolution. When Tesla finally rolls out the Model 2 with an aluminum-ion pack, they aren't just trying to offer one more EV. They're aiming to build a platform that avoids the risk of reliance on a foreign power controlling your battery's raw material and refining pipeline. Although lithium-ion remains dominant today, its supply chain bottlenecks and geopolitical risks suggest a ceiling on how far costs can be reduced and how independent EV makers can become. Aluminum-ion offers a new frontier, a chemistry built on materials that are widely available, globally diversified, and less constrained by strategic choke points. For Tesla, that means lowering costs, gaining supply chain autonomy, and offering a battery that isn't hostage to geopolitics. The supply chain countdown. How can aluminum-ion really be ready for the 2026 Model 2? Tesla has laid down enough breadcrumbs to make the 2026 timeline at least plausible. Elon Musk has repeatedly hinted at a next-gen chemistry for Tesla's low-cost platform during earnings calls and closed-door investor sessions, and in the past year, multiple battery patent filings and supplier leaks related to aluminum-based cathodes and solid-state electrolyte variations have surfaced across US and Australian registries. The timing matches market pressure as well. By 2026, global EV demand is projected to surge again, driven by sub-$25,000 models, and the only way for the Model 2 to hit its $17,799 to $19,999 target while undercutting gasoline on total cost of ownership is with a chemistry that charges faster, cycles longer, and scales cheaper than lithium-ion. On paper, aluminum-ion checks all three boxes, and that's why the industry believes Tesla might actually pull the trigger during this window. But this is where excitement meets gravity. Scaling a new battery is the single hardest step in this industry, and history is full of chemistries that looked revolutionary in the lab, but collapsed on the factory floor. Aluminum-ion will face the same hurdles. Mass production brings yield loss, integration complexity, and early-stage cost spikes that do not disappear overnight. Even a world-class manufacturer like Tesla must prove it can industrialize a next-gen cell at gigafactory volume, and the company will have to do it without slowing Model 2 production ramp-up. The core truth remains unchanged. Lab not equal factory, and no breakthrough matters until it survives 24/7 manufacturing at scale. There is also the economic risk curve. Even if aluminum-ion is cheaper long-term, the initial cost per kilowatt-hour will almost certainly be higher in the first production phase, and Tesla will be racing the clock to drive costs down before the Model 2 hits its full global volume. That is why many analysts believe there is still a realistic scenario where Tesla launches the first Model 2 variants using lithium-based cells, then switches to aluminum-ion mid-cycle, similar to how Tesla phased in 4680 cells after first launching to 170-based production. So the honest conclusion is this: 2026 is possible, but Tesla must prove it at scale. Momentum, patents, and strategy all point in the right direction, but the supply chain will determine whether aluminum-ion arrives on day one or whether it slips to a later Model 2 revision once the Gigafactory line is ready. The technology looks like a breakthrough. The question is whether Tesla can industrialize it fast enough. Now I want to hear from you. Would you buy a sub-$20,000 Tesla if it charges in under 10 minutes and goes 1,000 kilometers? Comment 1 for yes or 2 for not yet. Which matters more to you personally, faster charging or longer battery lifespan? Tell me in the comments. Just 3 days ago, Trump hit every rare earth coming from China into the US with an additional 100% tariff. Right now, there are a lot of moving pieces in the supply chain for Tesla's insatiable battery demand. By 2026, they'll roll out millions of affordable Model 2s, robotaxis, updated Model 3s, and Cybertrucks. Elon Musk obviously won't sell them with a lithium battery inside. Instead, in the R&D labs, hundreds of tests are running on the 3 latest battery technologies: aluminum-ion, salt-ion, and solid-state. Some internal leaks we've stumbled upon show that Tesla's making some huge advances that the whole industry thought impossible. All the new cells are getting more efficient, more powerful, while the prices are going down. Now let's dive right in. How Tesla is overcoming the energy density limitations of aluminum and sodium batteries. 2025 is when people talk about aluminum-ion and sodium-ion batteries for their advantages over traditional lithium in safety and price. Both use salt-based electrolytes and have a very stable chemical structure. Aluminum and sodium ions don't react easily with air or moisture. This basically removes the risk of fires or thermal runaway that lithium batteries are known for. More importantly, their production costs are significantly lower. Aluminum batteries cost only about 60% of lithium batteries, while salt batteries can even reduce the cost by 25 to 30%. However, the inherent weakness of these two types of batteries lies in energy density. Tesla's current lithium-ion batteries reach around 250 to 300 watt-hours per kilogram, giving the Model 3 or Model Y a driving range of about 350 to 380 miles per charge. In comparison, aluminum batteries only hit around 150 to 200 watt-hours per kilogram, and sodium-ion batteries about 120 to 180 watt-hours per kilogram. So, with the 75 kilowatt-hour battery pack, an aluminum-powered EV could only go 250 to 270 miles, and a sodium-ion one around 220 to 240 miles. That's the main reason most Americans still don't see these two as ideal replacements. They'd have to sacrifice too much driving range, especially people living outside the city who drive long distances or travel between states where charging stations are still pretty sparse. However, According to some leaked data from Tesla's R&D labs, the engineering team has found a few new ways to increase the energy density of both aluminum-ion and sodium-ion batteries. For aluminum-ion, Tesla first tried increasing the pack size to 100 kilowatt-hours, even 120 kilowatt-hours, but that will affect Tesla's structural battery pack's deskin. They also used graphene as the anode material to improve ion conductivity, but while that helped speed up charging and heat dissipation, it didn't do much to boost energy density. The newer and smarter approach they're working on now is something called 3D porous electrode architecture. Instead of adding new materials, Tesla redesigned the entire internal structure of the battery cell to make better use of ion storage space. In older aluminum prototypes, the flat anode and cathode surfaces only stored about 60% of the available aluminum ions. This time, Tesla built a nano-porous electrode network, packed with millions of holes just 5 nanometers wide. This design increased ion storage efficiency from 60% to 95%. Energy density rose from 200 watt-hours per kilogram to around 450 to 480 watt-hours per kilogram. If used in a Model 3, that could mean a 500-mile range per charge, 0 to 80% fast charge in just 4 minutes, and a battery lifespan of up to 12,000 cycles with only 8% capacity loss. A similar space optimization approach is being used for sodium batteries too. Since sodium ions are larger than aluminum ions, Tesla experimented with a layered electrode structure. In this setup, 10 nanometer sodium layers are stacked like sheets of paper to store more ions in the same volume. The result, energy density increased from 180 watt-hours per kilogram to around 270 to 310 watt-hours per kilogram, about a 45% jump. With a 75 kilowatt-hour pack, a sodium-powered Model Y could reach up to 380 miles per charge, almost the same as today's lithium models. But as sodium-ion batteries are cheaper, safer, more stable under extreme temperatures, and can charge twice as fast, they're still better than lithium ones. So if you've been skeptical about aluminum and sodium batteries, maybe Tesla's latest breakthrough will make you think again. Would you want a cheaper, safer, and more stable battery that doesn't compromise on performance? Which one would you like to see first in Tesla's 2026 lineup, aluminum or sodium? Drop your answer in the comments, and let's talk about it. How will Tesla lower the price of solid-state batteries in the next 8 months? At this point, solid-state batteries are still seen as the peak of energy storage technology. They have the best performance among all the new types of batteries Tesla is working on. We're talking about an energy density of around 650 to 700 watt-hours per kilogram, which could mean a driving range of 800 to 850 miles, almost 100% safety, up to 20,000 charge cycles longevity, and the ability to fully charge in just 3 minutes. For anyone who owns an EV, there's really no reason not to want solid-state batteries. However, the biggest problem right now is their very high cost and the challenge of mass production. The main reason solid-state batteries are hard to scale up is that they require a complete overhaul of existing manufacturing lines. Traditional lithium-ion factories use liquid electrolytes, but solid-state ones need a completely dry environment and high-precision equipment like vacuum presses, differential heating furnaces, dry rollers, and humidity control systems. That means replacing all the current mixing, coating, and cell assembly machines. Upgrading to that kind of setup could cost $1 to $2 billion, pushing production costs to about $400 to $500 per kilowatt-hour, roughly 4 times higher than lithium-ion batteries, around $115 per kilowatt-hour. That means just the battery pack for one EV could cost up to $20,000, keeping solid-state tech stuck at the prototype stage instead of reaching mass production. Other companies like Toyota and QuantumScape have rushed to announce that they're close to finishing solid-state development, but in reality, their prototypes still face issues like dendrite formation damaging cells, and interfacial instability hasn't been solved yet. This is where Tesla's quiet advantage comes in. The company's 4680 battery with dry electrode technology is already about 70% compatible with solid-state production. That means Tesla doesn't have to rebuild its entire production line. They only need to upgrade solid press machines and pressure control chambers at an estimated cost of around $200 million, compared to $1 to $2 billion for others. In its Nevada tests, Tesla already produces about 80% of its solid sulfide layers in-house, cutting cell costs from $200 per kilowatt-hour, if outsourced, down to $90 per kilowatt-hour. On top of that, Tesla's vertical integration model lets them make almost everything themselves, from raw materials to battery cells, instead of depending heavily on partners. They still work with Panasonic and Samsung, but mostly for R&D, not as sole suppliers like Toyota or Volkswagen do. Tesla now has one battery factory fully operating in Nevada and another under construction in Texas. Without supplier markups or supply chain delays, Tesla can reduce production costs by another 30% and roll out new upgrades within months instead of years. With this pace, Tesla could bring solid-state battery costs down to around $150 per kilowatt-hour by 2026 and even reach $100 per kilowatt-hour by 2027, the golden break-even point, where solid-state batteries finally outperform lithium-ion ones in both cost and performance. That would open the door to mass production and make this technology the new standard for the entire EV industry. How will Tesla's new battery technologies be applied to its upcoming model lineup? The fact is, Tesla's building a more diverse ecosystem than ever. From compact, affordable city cars to high-performance monsters built for long-distance driving. The big question is, how will they integrate all three new battery types, aluminum-ion, sodium-ion, and solid-state, into their upcoming lineup starting in 2026? We guess they're planning to mix and match them smartly, depending on real-world needs, climate, and budget, to optimize everything from cost to performance. Aluminum and sodium batteries will be the first to go commercial, powering Tesla's lower-cost, city-focused models. With the limitation of improved energy density overcome, these two technologies have completed testing steps and are preparing to transfer to mass production. Their cost is incredibly low, about $45 per kilowatt-hour for aluminum and $30 per kilowatt-hour for sodium. These two new batteries are expected to debut in the long-awaited Tesla Model 2, the company's compact, budget-friendly EV. According to internal plans, Model 2 will be unveiled within the next 4 to 5 months and start deliveries in Q1 2026. The standard aluminum battery version will be priced between $17,000 and $19,000, offering a solid 400-mile range, perfect for daily driving in big cities across the US, Europe, and Asia. Meanwhile, the sodium battery version, priced around $15,000 with 320-mile range, will target colder markets like Canada, Northern Europe, and parts of North America, regions where traditional lithium batteries still often lose up to half their performance in freezing conditions. Both battery types are also expected to power the upcoming Tesla Robotaxi, set to launch in Q3 2026 at around $20,000 per unit. With their low cost and long lifespan, these batteries could bring Tesla's operating costs down to just 15 cents per mile, making large-scale robotaxi fleets financially sustainable. On the high-performance side, solid-state batteries will power Tesla's premium lineup. The technology could make its way into the Model 2 Performance Edition by 2027, with a price of around $23,000 and an estimated 650-mile range from a 75 kilowatt-hour pack. Many insiders also expect the next-gen Roadster, coming in the first quarter of 2027, to feature a 100 kilowatt-hour solid-state pack that delivers up to 700 miles per charge and 0 to 60 miles per hour in just 2.3 seconds. That's the lowdown on Tesla's next-gen batteries and how they're making upcoming Tesla EVs safer, faster, and cheaper for every type of driver. Now it's your turn. Which battery would you trust under your hood? Drop your pick in the comments to let us know. If you found this helpful, hit like, share with your friends, and we'll see you in the next video.